this is where we left off. So let me get everything set up. I do have a 3D printer running in the background too. Hopefully the background noise isn't unbearable. But we'll pop out the chat so I can see it. And we'll go to live chat so I can see everything. Cool. Bring Discord up too in case there's questions there. There we go. Okay. All right, James is joining in. Cool. So yeah, this is where we left off last time. We set up all of our constraints. We went through, did all the equations, and then we went through the tedious process of actually creating the front and rear control arms. So today's goal is to first create the bell cranks, front and rear, and I'll show. In the rear we'll do push rod, and the front we'll do pull rod, just like we did in 2021. So you'll be able to see how to do both of them. Pretty straightforward process, generally speaking. And well, the bell cranks will be kind of different types of bell cranks, so we'll go through all that. So we'll do bell cranks. We'll also show how to evaluate things through the full sweep of motion, so from full droop all the way up to full compression. Be able to pick out key measurements that you want within the software and be able to just go through that. If you want to plop them into Excel and plot some stuff, again, you can also just export all of these XYZ coordinates of all of these points and create a model within SimScape Multibody. The last thing we're going to cover is steering, and then that'll pretty much be it. We'll be done with the suspension geometry, or at least the process that we took to create the suspension geometry within the 2021 year. Maybe I'll talk a little bit towards the end about areas where we could improve. So that being said, let's dive right in. We're gonna, we have our demo file up. We also have last year's suspension geometry here, so we can see and reference back exactly what we did. Because especially with the bell cranks, things are going to get really confusing. So one of the things that we're going to start out with is trying to figure out where really do we want to be placing. That's weird. Where do we want to be placing our bell cranks themselves? So at least in 2021, we made our bell crank pivot. I think it was offset from. Actually, no. It looks like it was exactly in line with the rear axle. Or no, we just used. Okay. So what I did here, at least last year, what I did is I created. We could set up the links, but there's only one other video in the series so far, so I'll take a look. So first step is to create the axes that the bell cranks are going to rotate around. In last year, when I did this, I just set up kind of something that looks like this. Some height that we're going to be mounting the bell cranks at, an angle for a pivot point as well, so an angle that the bell crank is going to be rotating around, and then we have our overall width, and those are kind of the dimensions that we need to define here. I'm forgetting some of my keyboard shortcuts. I've been in another design program all day. All right, so again, main things you need to figure out here are your overall width between your two bell crank pivots. So let's say this is going to be 350 millimeters. We need to see how high up this is as well, either off the ground. You can also measure, off of the chassis, lower point, whatever points you have to measure off of. But things that are going to affect where you position your bell cranks are things like where your differential is, where your chassis members are. All sorts of stuff can affect this. So we'll just say 370 millimeters above the ground for that. Again, these are just ballpark values, but these are things that you'll want to consider. Next, what we're going to do is we're going to create a line that goes like that. And what this line is going to do, it's going to be coincident to this bottom point here, and then it's also going to be perpendicular to that. And that's what's going to set our angle, or at least in my unprofessional opinion, what the optimal angle is going to be for the bell cranks. My reasoning for this is that our suspension is going to be operating right around ride height, and remember we set up our control arms around ride height, so that's generally where the suspension is going to be. That's where the springs are going to oscillate around that area. We'll say it that way. You'll press some, they'll extend some, and basically as the suspension travels, this angle is going to stay the same, but the angle between our push rod and this pivot is going to be different. And so, kind of as this travels in bump, this angle is going to, or the angle between these two lines that's included is going to become less than 90 degrees. What that's going to do to the bearings that are in your bell crank, and actually I guess I shouldn't really directly go off this. This would be the theoretical middle point of the bell crank. But yeah, essentially, if you have a force going into your bell crank that isn't exactly planar with the bell crank, it'll cause a force that is axial along the bearing. And generally, if you're using just deep groove ball bearings, that's not the kind of force they want to see. They want to see mostly radial forces. So that being said, if we, again, we're going to kind of back up a little bit. This line here, the height of this line needs to be the middle point of your bell crank. So this is just going to define that bell crank plane. It's not so much going to define, kind of the lowest point of the bell crank or the highest point where it's actually going to mount. These are just theoretical geometry constraints. So again, if you kind of set this sketch up in advance, you can always go back in here and say, all right, well, this is where we set up our bell crank axes, or maybe like bell crank packaging or positioning is something that you could call this sketch. So yeah, again, by setting this line up here, going from the end of our lower control arm to the middle of our bell crank and making it perpendicular to the axis that the bell crank is going to be rotating around, we can say that generally speaking, the axial loads on the bearing are going to be minimal, because at right height there are going to be none. All the loads going into the bell crank are going to be radial loads, and then when we oscillate around that, they're going to be very, very minor and still within specification for our bearings. Conversely, one of the other things that you can do is you can set this up to be more biased towards bump, because that's when the axial loads are going to be stronger. So instead of making this perpendicular, one of the things we can do, and get back to a normal view here and zoom in. Okay, so one of the things we can do is we can set up this angle to be, let's say 88 degrees. Just as an example, if we really wanted to go even further, one of the things we could do is we could bring in our rear suspension front view. So we could show that sketch. We can hide our control arms for now. So we can see there's that line. What we can do is we can create another line that goes here. Maybe we'll just convert this just to be consistent. So we'll convert that and we'll hide this sketch. So we'll make this some construction geometry. I'll get rid of this line too for now. Yes. So I can just say, I can make these two equal length first. There we go. And then I will dimension the distance between these 2 points to be something like, maybe half an inch. And, technically the movement of the outboard lower control arm point isn't exactly the movement of the wheel itself, but it's pretty close. And so, like I said, we can set this up to bias a little bit more towards the bump travel of the suspension by saying, hey, right around, I want the axial loads to be 0 halfway through the bump travel. And then again, making these perpendicular. Cool. So that's something that you can do. This isn't something we did last year. This is something you can do. It might make sense too, depending on how much force you're actually going to be experiencing through your bell crank. So keep that in mind. I'm just kind of giving a few options here. So this is how you would set that up. You'd convert the lower control arm, you'd offset it, you'd say by how much, and then you'd make those perpendicular. And then just to kind of, another thing we can do is we can show exactly what this angle is, just with a driven dimension, so that when we manufacture, we can kind of see, all right, well, it's 63.27 degrees. This is at 63, so we're pretty close. And actually, just out of curiosity, what would be the difference here? Or I guess I don't really need to do that. I can set up a difference between just these two. So we're looking at 1 degree of difference. So again, this isn't like, we're looking at 1 degree of difference in our bell crank axis. It's not really going to matter all of that much. But again, we're working with theoretical lines here, so keep in mind how much you really want to go in, how much you really want to look into all of this stuff. So, all right, cool. So we've set up our 2 axes here, and just to make me happy, I'm going to make this line an arbitrary dimension of 100 millimeters. Again, we're just setting up kind of an axis that our bell crank will rotate around. So we'll rename the sketch bell crank axis, or I guess we should say rear bell crank axis, and packaging, because we did look into, all right, well, where is this bell crank actually going to be located? So we'll have to look at our rear assembly for that. So we just have our 2 axes here. And then next thing we need to do is create a plane. And that plane is going to consist of this point out here. Actually, we're doing this at right height, so we need to make sure that we're selecting the right thing. Our right height point is that lower one, so let's go again, plane. And actually, one thing I will do is I will make sure, where is it at? Both sets of control arms, there we go. So we will have plane going along that point, and then also that line, and we want the plane to be perpendicular to that. You can also see that the normal is pointing down. I like to have the normal pointing up that way, so you can use flip normal when you're constructing a plane to make it, so that when you actually start your sketch, you're looking down on the part like this instead of looking from underneath. All right, so again, this is kind of our plane that we've set up here. Actually, now that I think about it, we should be using the above point. I'm trying to compare this to what we did last year. So we should be using the point that is actually along this line here, because that's where all of our geometry is going to be created relative to. So we'll do that. So again, if you're setting things up at right height, just use the lower control arm point. If you're setting things up above right height, use the point of the control arm that you kind of set up here. So we'll do that. Although, does that really make sense? Let me take a look at what we did last year just a sec. So we did our pivot positioning. And then we did both of our bell crank geometries in one sketch. It's taking me a minute here to remember what exactly it was that I did. Okay. Okay, yes. So yeah, we want to set this up theoretically, actually. Yeah, okay, so what I did last year, and I'm not saying that this is the exact best way to do it. There might be some better ways to do it, and that's kind of why I'm struggling with this right now, is because I'm trying to figure out why I thought it was a good idea to do it that way. Basically, all we're doing is we're creating a plane right here, right at that center point, and then whatever this vertical line is that we just created our axis, we're just referencing off of that. So we're saying, okay, so here's this plane that we just created, and this is our rear bell crank mid plane. That's what we're going to call it, because again, remember, this point here defines the middle of that pivot, and then the other thing we're going to do, or at least that I did last year, is I set up a sketch here that said here's where our pivot point's going to be, and I'm not sure that that's necessarily the best thing to do. Kind of if you look up here, what I did was the pivot position. I just created that sketch in advance, and then I went through my bell crank geometry. I think there's going to be a better way to do that. Yeah. We're just going to say there's going to be a better way to do that. Cool. So the other thing that we need to do, like I said, in the front or in the rear, we're doing a push rod setup, and also in the same setup, we're doing something where the shock absorbers kind of face this way. In the front suspension, what we did was the bell cranks were just kind of simple rockers where the suspension was vertical, rather than kind of this pivot motion. Hopefully this makes sense. So in that case, we needed to set up this offset normal and all sorts of stuff. Here, we're just going to set up a plane where the bell crank pivot is going to reside on. So, and yeah, like I said, we'll set up that pivot, and really, at least what I did last year, I think, if I remember right, this front bell crank plane was not too far away from the front offset, or the wheelbase. Yeah, so in this case, I made the bell crank plane relative to the rear plane. That kind of makes sense, but yeah, we'll do that. So we'll just create a plane going off the rear axis center line, in control, click, and drag to easily offset. And we'll just say that, yeah, we want the center point, or the center plane of our bell crank, to be pretty much right around there. You could reference this off of the front wheel center line, but then if you wanted to move it behind, like if this plane ends up behind the wheel and you wanted to move it in front, you'd have to flip the offset. Might not be a big deal, but this way you just have one value to change back and forth. Potato. Cool. Main thing we need is a front bell crank mid plane. Cool. All right, and now we can launch a 3D sketch, and we're going to start creating the bell cranks themselves. So we actually don't need this for now. And yeah, I guess I'll go through kind of my philosophy when I made the bell cranks. My idea was to create create all the bell crank geometry at full droop, and then evaluate it at ride height, and then kind of go back and forth from there. The reason for doing full droop to start, it made it really easy to say, all right, well, at full droop, and we'll kind of go towards like wheel rates and stuff with like progressive bell crank or progressive wheel rates and all that sort of stuff that we decided to do. Basically, my theory or my approach to this was to say, all right, at full droop, our spring is going to be fully extended, so there's going to be no force. So I know the total length of the spring damper system. I know where my control arm is going to be at full droop. It's going to be, my wheel is going to be 25 millimeters down, and from there, pretty straightforward. yeah, so I can kind of offset from there. So you can do this a couple of different ways. You can design everything at right height and say, here's, I know what spring rates I'm already running, and I'm going to do 500 pound per inch springs. So with this amount of compression, this is what my spring is going to be. These are the force balances. Again, for me, it made a lot of sense to just design everything at full droop. So we'll go through the process of creating something at full droop first, and this is where it gets really tricky. Because we actually need to bring in our rear wheel if we really want to be 100% theoretical about this, and how this is actually all going to work. So what we're going to do, and this is going to be pretty fun, is we're going to recreate a few things here. So we're going to be on the YZ plane. We're going to recreate these 2 points here, or sorry, those 2 lines. We'll just make them equal length as we go. And the other thing we're going to do is we're going to constrain these to be on this plane. So basically what we're saying is, well, and I guess technically this, I'm realizing that technically this isn't 100% accurate. So again, to kind of back up and kind of let you guys peer into my head a little bit, at some point you have to say, this is enough of an abstraction, and the amount of decimal points I'm going to chase by making things exactly the way that they should be, it's insignificant. It's going to be 0.1 of a degree off or something like that, and that's imperceptible in terms of manufacturing. So yeah, at least without creating a full upright in here and mating everything in an assembly and then going from there, we're going to make a couple of abstractions. One of them being that the wheel is always going to go perfectly up and down along the... actually, I guess we don't need to do that. Hold on. I think if I remember what I did, so this has that, and this has on plane. We're going to remove that. We're just going to make these parallel. So we're going to work through things until we get reasonably close to a fully defined sketch, and from there we can make some assumptions. But again, remember that what you have to do, you're making abstractions, you're starting to build things up that are this is pretty close to a suspension. This isn't exactly the suspension that we're making, but it's pretty close. So yeah. So a couple things we got to do. You got to start playing around in 3D space. If any of you guys have ever looked into triangulation and what it takes to fully triangulate something, you'll start to see some parallels going here. And for that, actually, what I do need to do is make I do actually need to make the full suspension, or the full tire here at least. So yeah, we're collinear there already. We're going to make these equal length. Okay. So essentially what we're going to do is we're going to create 4 lines. And again, these are just construction lines. And in this case, they're going to that lower control arm point right there. Then the other thing we're going to do is we're going to do the same thing for the top. And you'll see why this is important in a little bit. Again, if you know anything about triangulation, you know In order to triangulate something in 2D space, you need three kind of areas where you're observing, or 3 points where you're observing from, and you need to know the distance from those 3 points. In 3D space, it becomes 4. So basically what we're doing is we're using the geometry of the tire to triangulate kind of where it needs to be in 3D space. And again, I'm kind of thinking that this might not be exactly correct. Again, just to be safe, I'm going to go through and delete all of these parallel constraints here. We'll go through and add them in later. And I should also clarify, this isn't exactly what I did in 2021. I'm just finding ways to make it better theoretically as I go along. Cool. So we've just created the spiderweb mess. It'll all make sense in a bit, hopefully. We're going to create 2 copies of our control arms here. And we're going to sketch these starting on the XY plane. And we're going to be very careful about, for some reason, I can't double click fast enough to stay within the line tool. There we go. So we created something that looks like a control arm, but the reason that we're being, why I didn't create them, exactly the same length or whatever else, is I want to be careful about which relations I add. And this is kind of going back to kind of what I mentioned in last episode. In 3D sketches, you want to be very, very cognizant of when you're adding a relation that's coincident, equal length, parallel, collinear, all this kind of stuff. You want to pick and choose when and where you want to use those. You don't want to use them just because it makes, just because it's there and it kind of is the same. Now you want to be very careful. So what we want to do here is we want to create something that, or a line that is coincident just at the pivot point, and is the equal, and that this geometry is the same as that control arm. We want it to be equal length, but we want it to be able to swing all the way forward. If I made this point here coincident there, if I made these collinear or anything like that, or if I just use like convert entities, it won't give me the exact behavior that I want. So again, we'll go equal length there, and then we'll also go equal length here. And now we have 2 control arms. We're going to intentionally drive them down super far, and then we're going to create a center line here. Cool. So this center line is going to be equal to that one. And actually, really, I almost want to do this in 2 separate sketches, just to make things easier to see later. But we'll keep them in the same sketch for now. Make those 2 equal length. And then what we'll do is we'll start to piece all of this together. So I'm going to create my 4 lines that go to that point first. Again, we're making kind of like a spider web of stuff that will hopefully all make sense. Right, equal length. And make sure you're pairing them up properly. And equal length. And that one. Equal length. Cool. And if we move it around a little bit, kind of start to see that it's going to eventually behave like we want it to. So again, I'm going to drag this somewhere to where I can see still what I'm doing to some extent. Maybe I'll drag that back down there. And then again, if we want to see which relations we've added, we can turn that on. We can see, all right, cool, we have an equal length there. This thing has an equal length, this thing has an equal length, and that thing has an equal length. You can also check the relations in the left sidebar. All right, let's finish up this spaghetti. So again, we did our top one. Now it's time to do the bottom one. And hopefully once all this is done, we'll have, again, our goal is to be able to create something where we can move a wheel up and down. Actually, now that I think about it, this is way too much work anyways. Yeah, it's all right. We'll make do. We're good. Yeah. Okay. So we have our points going to the lower control arm, and this is going to be, again, kind of pick and choose, trying to pick the right points or pick the right lines. Again, that's lower control arm, equal length. Lower control arm, equal length. And this is also lower control arm, and that's lower control arm, equal. All right, so effectively what we've done is, let me just hide everything else here. We've created a wheel and tire that can very, very roughly move with our suspension here. Hopefully I didn't just add a coincident constraint somewhere where I just drag that. Yeah, so we can move. Can we? Yeah, so we can move this up and down. You can see the wheel will move geometrically. Nothing will change relative to that upright. Those 2 points. The 2 control arms will stay the same distance apart, and then the wheel and tire will stay aligned to it. Yeah, and you can see kind of where this starts to go haywire a little bit because we don't have a toe link in here to control it. Yeah, so I guess this doesn't entirely make sense to do. Cool. We're going to, gonna abandon that real quick. Just take a quick peek at how I did it last time. Yeah, I think what I did last time was I'd created these discrete points. And this is kind of, you can actually see in this sketch, you can see some of the same stuff where I'm creating these triangles and all sorts of stuff to see, all right, cool, here's my wheel center line, it's going to stay parallel, this is going to move down that much, so on and so forth, in full droop, and same thing with full bump. We'll do a slightly different simplification here. Again, we're doing a simplification. I kind of took that last exercise, hoping that it would kind of get us to a point where we didn't have to simplify quite as much, or maybe it showed some insight for somebody, but I don't know. Kind of a bit of a waste of time. Moving on. What we're gonna do this time is we're gonna keep it super simple. What we're gonna say is this wheel and tire is gonna be, it's not gonna move forward, backward all that much, and really, this lower control arm point. How do we want to do this? Sec. Yeah. Okay. What we're going to do, made up my mind. We're going to make 2 control arms really quickly on the XY plane. All right. And I think this is going to be pretty similar to what I did in 2021, but this should be a reasonable enough abstraction that we can keep moving forward and not spend too much time on this. All right, so move that down, create a little upright bit there that connects those 2. The other thing we're going to do is we're going to create something that looks like this. going to make these two equal. And then we're going to create a couple more construction lines that are exactly the same on the YZ plane. Equal and equal. We're going to abstract and say that this point is going to be on this plane. I'm just going to say again, the wheel didn't really move too far forward, backward. And then the difference between those 2 points, the wheel center line, and we're going to use the tab key to make sure, you see by my pencil right now it says Z, means that we're doing this dimension along the Z axis. And we're going to say this is going to be 30 millimeters down. All right. So again, the center point of the wheel here has moved 30 millimeters down. We're now in full droop. And technically by rules, you have to design for at least an inch of droop. So in 2021, we design for 30 millimeters of droop and 30 millimeters of bump. So same kind of thing here. We'll set 30 millimeters. If you want to narrow those margins, you can do 28, 27, 26, all the way down to an inch. But yeah, so now we have our control arm at full droop. Again, this is an abstraction. This is very simplified. This doesn't fully take into account how exactly this point's going to move. All that to say that all that time I spent in the last 3D sketch, didn't really need to spend that. You don't need to spend that time doing it. But again, keep that in mind that you are making an abstraction at some point. So we're going to go on the XY plane again, design some control arms up here. This one looks like it got an axis constraint put on it. Equal length, equal length, equal length, and equal length. Cool. So now we have, we've got 2 more control arms up front. Same thing. We're going to hide the rear wheel entire. We're going to show the front one. Going to do the same exact thing here. We're going to go center line between those 2. It's going to go out to that point and then up there. Same thing here. Out, up. We're going to make sure that that point is coincident with the front axis, front axle centerline plane. And then we're going to make all these equal to each other. Jeez, my nose is really itchy today. Cool. So that's equal. Those 2 are equal. And then these 2 are going to be equal as well. All right, and then we'll make, again, another dimension along the z-axis between those 2. For some reason, it just really freaked out there. Again, 30 millimeters of droop. So now we've created our drooped out control arms. Jeez. Okay, so 2 control arms, one at 30 millimeters down on the front, one at 30 millimeters down in the rear. Right, from here, we can start work on the rear bell crank. And I'm actually going to exit out of this sketch and just say droop control, or control arms in droop. Okay. Actually, we don't need to hide that yet. We can show that. We can hop back into a 3D sketch here. All right, so now our goal is to actually make the bell crank geometry itself. So we can get rid of those control arms. We just need the control arms in droop. Again, in the rear, we're doing a push rod, so we'll start with that one, since this is kind of the more conventional one. Essentially, what we need to do, we also need to bring in this pivot back again. Could convert it. Right. So we have this rear bell crank mid-plane. We're just going to start off by making a theoretical bell crank. And what is a bell crank other than just 2 levers around the same pivot? we're going to make both of them lie on this bell crank mid-plane plane. Make on plane. Cool. From here, we're going to draw a theoretical line. This theoretical line is going to go down right to that control arm point. It's very important that it goes to the point and not kind of out somewhere else. At least from my experience, if you're going directly to the node of the control arm, then you are minimizing the bending loads on the control arms themselves because it's going to that spherical joint. It's in line with it. That's where it's going to get reacted. There's going to be no reaction moments on any of the spherical joints. If you push down in the middle of the control arm, it's going to give you a bending moment or kind of off of it. So keep that in mind. So we have that. Again, things look kind of weird right now. Let's draw them in a little bit more proportion here. So we have we have our two bell crank pieces there. We have our push rod linkage here, and then we have a damper going back that way, and that's it. We're done. No, so this is just the initial setup. From here, it's going to get pretty tricky, and again, you're kind of going to need to know. Well, we'll need to have one of the future steps done, and we'll have to come back to this. It's going to be a little bit iterative. You have to trial and error a few things. At least how I did it. Again, you can export things out into a simulation in Simulink if you have one. So what we're going to do is we're going to define a initial position, basically at full droop. What does this look like? So in this case, I think we'll make this angle here. Let's make this angle something like 75 degrees. So it starts actually maybe like 65 degrees. Cool. So we'll have that there. And then here again, we're using kind of this old reference line that we had. And we'll make this starting at 10 degrees maybe. The other thing we need to know is, well, how long is our spring damper at full droop? And in our case, I know that it's 200 millimeters because we're using the Öhlins dampers with a 55 millimeter stroke. And then you decide how long your lever arms are for your bell crank itself. So let's say maybe 45 millimeters here, 35 millimeters there. And again, this is stuff that we're just setting initial values here. We're going to have to come back to this and kind of actually thoroughly analyze it. Again, another thing that I would recommend is making this other mount or this spring damper on the plane with the bell crank. This way, again, you're minimizing the amount of radial loads, and then now you just have to figure out, well, where can I actually mount this to the chassis? And you can do this in a few ways. Or I guess that was one of the things I was going to come back to. So we're going to make that not actually coincident, and we'll have to do a few things differently here. Hold on. I just remembered what I was going to come back to. So earlier on, I mentioned that one sketch that I made that just said, "Hey, move the bell crank pivot back." In my opinion, what we should actually be doing instead is saying, all right, well, here's the distance between, here's how far outboard the damper mount's going to be, and let's say it's 175 millimeters. And then, we'll pull up our, if you remember, we had our chassis sketch. So we'll show that. And we'll say, all right, well, here's our front control arm, or here's our front mounting point for our rear control arm. And really, we want this to be kind of, maybe spaced out a little more from that. So we're going to move all of this back. And it's going to look really weird for a little bit here. It's going to move all this back. We're going to say, all right, so between here and here, and then again, we're going to tab, hopefully. And maybe it won't let me, so we'll do something instead that looks like this. Go again, center line here, and we'll go along, along Y. This will come out to there, and this will pierce that. Okay, so basically what we're trying to say is, all right, well, how far from that front bell crank or front control arm mounting point is this going to be, and then how far outboard is it going to be? So 175. So now I figured out where our damper mount is, and then again we can create our reference angles. And what I'm actually going to do is actually no, that makes enough sense. Yeah, so we'll do get an angle between those two. Reference to start is going to be 10 degrees, and then this angle here, maybe. All right, cool. And now we just have to figure out whereabouts we want this pivot point to be. And if you remember, we kind of set this as our width in the past. So really, all we have to do from here is go this way, and then just make sure that this is along X, which is our front to back axis. So this way, remember, this line drives the width. We figured out kind of how far back our bell crank needs to be, and we figured that out based on our spring damper mounting point, because what we found is that actually kind of played a little bit more of a role, and it was actually important where that was. This is also important, but in our case, we were using 2 big aluminum plates for our drivetrain, and our drivetrain carried our suspension, so we had a little bit more flexibility there. But again, these are design decisions you can make. Actually, you know what makes more sense? Instead of defining this to that, we're actually going to define the angle between the push rod and its lever at resting, and then same thing here between the damper and its lever arm. Again, or not at resting, at full droop. Also, tip here: if you notice the icon right next to your dimension when you're making an angle, it has that little lock button, and the right mouse button is hovered. If you click the right mouse button, you can drag your dimension anywhere. If you didn't click it, it would create all sorts of these other angles that you might be interested in. So if you know it's like, all right, well, I want 67.2, but I want to put the dimension somewhere else. In 3D sketches, it freaks out a bunch, but in 2D sketches, it works really well. So yeah, or maybe we'll do, I don't know, 80 degrees at full droop. Actually, no, let me think. Yeah, what you want is, we want this to be at like 65, and then we want this to be at like 100. Yeah, this is kind of all rough, and you'll need to play around with this and figure out exactly what your handling characteristics are like at ride height and at throughout. Maybe if you wanted to do a lap simulator. But again, these are kind of these are, I guess, the dimensions that you need in order to set things up. You need where your spring damper mount's located, the length of your damper at droop, 2 lever arms. So this is the distance between where your rod end's going to mount and the center of your bearing. Same thing here, where the end of the damper is going to go versus the bearing. Your initial angles, just to kind of figure out, all right, well, what's this thing going to look like at full droop? What are the angles between the two of them? And then that's it. It's pretty straightforward from here. So this is our bell crank geometry at full droop. We've created, again, these 2 lines are the ones that are important. So I guess I can make these 2 shorter, or construction geometry if I wanted to. But I'm going to leave everything in there because it shows the push rod, bell cranks, and the spring damper. So I think I'm going to split this up into 2 sketches as well. This isn't something I did last time, but I think it makes a little bit more sense. Rear bell crank geometry. Cool. We'll go ahead and hide that. We can also hide this front wheel and tire assembly. And then again, we'll jump into another 3D sketch. Get some water real quick. Cool. So the way we did our front bell cranks in 2021, it was different. I'll put it that way. Again, we're making use of progressive wheel rates, or at least what we understood about progressive wheel rates in order to do some of this stuff, and in order to simplify some things. That being said, well, I guess let me just build our front bell crank here real quick, and we'll talk about why this can be a good design and why it might not actually be that good of a design. And boy, does that look weird. What did I do? I think I was on the wrong plane. I need to be on YZ for this. Alright, I'm on YZ. Okay. Yeah, there we go. Alright, so we're going to... Oh, yeah, that's right. Okay. So, I'm trying to remember what I did 5 months ago, and it didn't make sense to me back then, so this is going to be kind of fun. Yes, okay. So, what we did with our front bell cranks is, again, kind of same thing. We have, I guess not really same thing. We had a pivot point that went this way. We had our spring damper mount offset, and then we had, again, our two lever arms sharing the same pivot point. This isn't necessarily the best bell crank design ever, but again, I'm trying to show you a couple of different things that you can do. It would be kind of boring if I made the same bell crank in the front. So we'll show you what we did in the front here. And actually, in this case, we ended up sharing the same pivot point. We just offset the spring damper forward. So, all right, let's just dive right into it. Essentially, what we have here, again, we have our pull rod, we have our pivot, we have our pivot axis, which in this case is normal, or is along the x-axis, so it's lengthwise along the car, just for simplicity's sake. And then we have our spring damper going vertically. This is parallel to, I'm going to just make this parallel to the front, to the front plane here. And then we're going to, we're also going to make both of these parallel to that. Actually, I have to do them individually, that's right. Or really, what would be best is to do this and that as perpendicular. Same thing there. Because remember, this is rotating around X, and we want these to be basically moment arms rotating around that. This we want to be parallel to this guy here. Technically, we could also make it perfect. Yeah, never mind. Really, what we should do is make it parallel to this. Or never mind. Yeah. Coplanar would be a better term here. Basically, we just want to make sure, again, as we were talking about before, we're trying to minimize axial loads. So, yeah, that's where we're at. Again, our unsprung dimension there. We're going to figure out where this thing is actually going to reside in 3D space. So So again, we said kind of where front bell crank mid plane is. That's really where this line is going to be, or this point here is going to be. And then we can also draw from here along YZ. So we'll make a line along Y and a line along Z, and this will be coincident with that. And then we can say, all right, well, where along our chassis do we want to mount our bell crank? And we're going to say, all right, well, it's going to be 50 millimeters off of the bottom of the chassis. Remember, not off the ground, but off the bottom of the chassis. And that's going to be 300 millimeters out. That's where we're going to have our bell crank. Again, for example, you can go through and edit all these dimensions yourself later if you're interested, or if you need to. Same thing, we're going to create our two initial condition angles. In this case, our pull rod is going to start at, let's just say 90 degrees. And of course, we also need to dimension the length of this arm. Drag that around. Cool. So that's there, and then we'll say that this spring damper system starts at, let's see, what are we looking at? 70 degrees, sure. 45 here. And then last but not least, we need to figure out where we're mounting our spring. So this is going to be vertical. Maybe. Or, yeah, why am I thinking vertical? It needs to be along Z. And, yep, that's right, because the spring damper is more further forward. Actually, because that one's already along Y, we need to do two separate movements here. Cool. So we'll make that along Y. That's already along X. Right. The other thing we'll need to decide is how much space we need between the pull rod and the actual damper itself. I think in our case we were doing something like 55 millimeters. Actually, that looks a little big. The 35. That looks about right. And then that's going to be also this line here. And so then we decide, all right, well, our spring's going to be mounted 330 millimeters away from the chassis. As right there. So again, a lot of these things, I kind of breeze through them, and I'm a little scatterbrained today after a long day at work. But we have packaging constraints in terms of where we can actually mount things to our chassis. So this needs to be 330 millimeters out that way. Our bell crank is going to get mounted 50 millimeters above the bottom of the chassis, and at this width away from the mid plane as well. Here's kind of the important things that are suspension driven rather than chassis driven are our initial spring length, and then these angles that we'll get to soon, TM, and how we can figure out what the best values for those angles are. But yeah, we have our basic suspension bell crank geometry. And just to make this different, not 90 degrees, we'll make it 85. So again, we've kind of gone through, we have our pull rod here, we have our spring, we have our bell crank itself, and this is kind of a weird shaped bell crank. Pull rod bell cranks tend to be weird from what I found, so keep that in mind, at least if you're going this kind where you're pulling on the bell crank and then your spring damper is mounted vertically here. I've seen various designs where the pull rod is pulling above the pivot point and then it's compressing a spring that's underneath the chassis running left to right. That's an option as well. But basically, you can design these a whole bunch of different ways. The main thing that you're trying to figure out is, all right, at full droop, my spring is fully extended, and then I want, we always want our push rod to be in line with that point there. From here, things get a little bit trickier. Yeah, we'll start diving into things. Actually, that's one of the things that we'll do first here, is we'll figure out one of the things we'll have to do at some point is figure out, well, okay, what's that? Where's our push rod actually mounting to? It can't mount. I don't know. Maybe it can, but generally speaking, it can't mount exactly to that spherical bearing. It has to be offset a bit. There's going to be some kind of bracket or some end to your control arm here that's going to pick up that point. How far away does that have to be from from that actual spherical joint? So we'll make this construction geometry, and that's where the actual spherical joint will mount to the control arm. We'll have, again, a control arm end here, whether it's machined out of aluminum or steel or however else you do it, but that's where it'll mount to the control arm. You can see that the line where the force is being applied is going to pierce that right there. So we'll save our document real quick. Things will look weird for a second, and we're back. Cool. And we'll go through and do the exact same thing for the rear here real quick as well. Let's exit out of the sketch using the D key. We'll say front bell crank geometry. And then we'll go back into this one. And again, here I'm using the split entities tool, which is kind of a hidden tool within Solidworks, or I guess it doesn't really show up on a lot of the default toolbars, but it's, I really like using that tool. So again, we'll make that construction geometry there. And yeah, from here, I think we're all set. Again, we've made our bell crank geometry, our push rods. We've made a push rod, we've made a pull rod. I don't need to edit that, I just wanted to show it. There we go. So, made both sets of control arms. We'll hide that sketch. We'll show both sets. Show both sets of control arms. We've made a push rod in the rear with this kind of bell crank. We've made a pull rod in the front with one where the spring is offset. Keep in mind this will create some bending loads somewhat within your belt crank mounts. So because you have two forces that are acting out of plane from each other, this is going to have some interesting or more complex reaction forces. Just keep that in mind. It's not inherently a bad thing. It's a compromise you can make. So we've done two types of bell cranks, two types of rods to connect them, and now it's time to put it all together and make the most challenging sketch that I've found, or I guess the most challenging 3D sketch of all of this, which is what I called parametric analysis. And again, it's pretty straightforward once you kind of get into it. So let's actually edit this sketch here so we can see what it is. And what else are we showing here? That looks like that bump sketch showing. All right. So we have, again, kind of that wheel simplification that I showed earlier. We have a couple of lines for triangulation up here to our push rod mounting point. We have a bunch of variables that we were measuring, and then you can see that the only driven variable was our wheel travel. And in this case, we did plus 50 millimeters just so that we didn't have to invert our dimensions. And that's something that gets tricky within SolidWorks when you're doing 3D sketches. Like if I wanted to do minus 50, it's going to throw an error here. So instead of setting our ride height at 0, we just said ride height's at 50 millimeters above a plane that we'll create here. And that's just so that we can go through and say, all right, well, this needs to be at 20 millimeters, which is 30 millimeter droop. And then, again, the opposite, which is 80 millimeters. That's our full bump. And that way, again, we can sweep all this. We can measure all these different angles. In our case, we put them in an Excel spreadsheet, then calculated a bunch of stuff in order to figure out what our bearing loads are going to be, what our wheel rate's going to be, how to size our springs and everything else. So you can measure these different values and start doing math and calculations. But after this point, basically, the design of the suspension stops and it becomes evaluation. And kind of the iteration on it. So again, this is the sketch we're going for. It looks pretty simple. It kind of is. Again, the key thing here is we're creating all of these all of these points with specific relations. And yeah, we'll go from there. So let's just dive right in. And we'll quickly save before we do that as well. Go right into a 3D sketch, grab some water. All right. Let's start with the front. We'll need our front wheel and tire. Actually, before I do this, let me think how I want to do this really quickly. Yeah, we'll just keep it the way it is right now. Yeah, so we're just going to do things on the left side and keep doing it on the left side. At the end, we'll mirror everything over to the right and just have a very clean sketch that we can then work from in order to create weldment profiles and whatever else we need to create. So again, remember our key point here is that we're using something that looks like that wheel. Again, we need to be on YZ, perpendicular to that. Cool. It's going to be equal and equal. Maybe. There we go. All right. We then need to create XY plane, create our two control arms. Trying to keep in mind where are things never going to move, which is at the main chassis side pivot points. Things are going to move out here, so we're not making any relations out there. We're just making equal length. Because again, the length of these control arms hopefully isn't going to change. Hopefully you built these out of a strong enough material to where the elastic modulus is high enough. You're not building your control arms out of rubber and they're deforming as you're going. Cool. Again, we're going to do the same thing here. We create this little triangle. And yeah, actually that was one of the other things that we did. Do I want to still do that? Yes, I do still want to do that. Give me a second, my brain's trying to work. Yeah, what we're going to do yes. Yeah. Okay, so we're going to create something like that. This is going to be perpendicular to that side of that wheel, and that's how we're going to make this all work. And really what we should have done is do that. So we'll create something that looks like that, and then something that looks, I guess, like that. We'll merge those 2 points together. These two will be collinear. Not in that way though. Did I do something wrong? No. Okay. I think I might have actually. Okay. Yeah, I was drawing on the wrong plane. All right. Let me back up a little bit here. Okay. Just do things the same way. Split the entities. Try not misclick. Oh, I'm drawing on XY, that's why. There we go. I want to be on YZ to start. And we'll do that. Okay. Make equal. Make equal. And we'll make. I must have deleted that one too. On accident. There we go. Alright, made those equal as well. I'm going to make these two perpendicular. And I'm going to merge these 2 points. And last but not least, what I'm going to do is I'm going to make, let me hide this plane real quick. Hide that one too. I'm going to make these two parallel. And same thing here. Parallel to the front axle centerline plane. So now, in theory, we have, oh no, I still need to make those two equal as well. All right, there we go. So now I can kind of drag this around a little bit. Let me see what that looks like. I think the other thing that I did was I made that point along the y-axis, or made this also parallel with front axle centerline plane. And the reason being, basically, what we're trying to do here is we're trying to move just the tire and figure out how the suspension responds to it. And again, at some point, this is going to be an abstraction, so we're not going to get exactly 100% correct kinematics. We're solving things based on certain relations, and we're trying to make some assumptions about how these things are related. This is a point. Yeah, again, we're trying to create things somewhat and evaluate things to a certain point. After this, it's a pretty good idea to run this through SimScape Multibody if you really want to get nitty gritty about how these. How the control arms and the wheel and the road and everything else all interact, or if you have some other kind of software to go through, that's also an option. So again, we've created this thing here. This is one corner of the car, and I can just move the wheel and tire around. And remember, the thing that I did is I made some collection of lines that connected things together in the static configuration, I guess. And actually, you know what I just realized? This is all in Droop, or the geometry that I'm showing is in Droop. So let me back up a little bit. I'm gonna have to delete some of these. So and that's one of the other things I need to do. Mentioned earlier, we need to create a plane off of the ground plane. We're going to go 50 millimeters below the ground. Cool. Move that up below that. Super descriptive title, I know. That'll come in handy shortly, and we'll hide the ground plane for now. All right, I'm going to hide both of these as well. We'll come back to them in a second. We have both sets of our control arms. Actually, you know what? Never mind. I'd done everything right. There's our Droop control arms. I doubted myself for a second. All right. Regardless of all that, we actually still need to create our plane offset from the ground plane. And we need to move it up below that, and might as well rename this. It's what I called Parametric Analysis. Okay, and we're going to go ahead and edit the sketch again. And we'll move this up to some height. We're going to select the midpoint of this. Or I guess we're going to go from here to the midpoint. And this is going to be our input for everything. So, and you can probably tell how fried my brain is today. But what we just did is we created front control arms and a profile of the wheel. And we referenced that to a plane that's 50 millimeters below the ground. And now what we can do is we can go down to 20 millimeters. And then we can also go all the way up to 80 millimeters. And if we're designing a Baja car, we can go to 150 millimeters or whatever else. Some pretty crazy suspension geometry. And you can see that this length and this length are the same. Its relationship to these 2 points is roughly it's roughly correct. Again, this is where we abstracted, is with these 5 lines right here is where we said, all right, we're going to do this in kind of a planar method in 2D. It's going to be, we're going to create these lines that are all equal length, and we're going to say that the length of those lines, the impact of the small change in length of those lines is so small that it's not as important, or it's not going to affect things significantly, at least to the kind of math we're trying to do and the kind of analysis we're trying to do. Again, ultimately, your proper thing to do here would be to just put together an assembly of a bunch of control arms, a wheel, tire, upright, solve everything through a proper solver or through a full assembly. But again, we're trying to do things within one file. Long-winded way of saying it doesn't matter all that much. Cool. So we can hide the wheel and tire now. We can also hide the control arms. We can show our front bell crank, which is already shown. And the tough part now is actually we will need to bring back our Droop control arms here. We'll need to make some more, I don't really know how to call them. We're going to make some lines. It's going to make some lines here. Make those 2 collinear. And then I'm going to do the same thing here. In this case, I'm just going to make them perpendicular as well. I'm just creating some arbitrary lines that I can fully define here. Cool. We're going to recreate those exact same lines at, let's see here. Let's just bump that up just so it's easier to see. So we're going to do something that looks like this, and we're kind of on XY plane, I guess. Cool. One of the other things I could do is I could also split split those two, but I'm not going to do that yet. Also, I can hide the Droop control arm points now. Hide that. It's a little easier to tell what I need to do. Equal length. Equal length. Equal length. This triangle that's identical, make that collinear. That collinear as well. Cool. Basically, again, we're just going through and triangulating where that point is in space. I thought that I had... Nope. Cool. So what we've done now is we've recreated where our pull rod mounts to the control arm. We've done that here relative to that point. Because remember, this isn't always going to be collinear. It's just collinear at a resting point. And theoretically, kind of this angle, you can adjust that if you don't want it to be exactly collinear. Then, kind of like what we were talking about before with the rear bell crank angle, you want to minimize those out of axis loads. So if you wanted to set this up for a different ride height, you could do that as well. Cool. That being said, let's go ahead and make, we're going to convert, actually we don't need to convert our pivot point. Just need to make, go on YZ, make that. Delete that as well. And then we're also going to make our spring damper system. All right, and this is going to be perpendicular to that. Nope, not collinear, perpendicular. And that's also going to be perpendicular. These two are going to be equal length. These two are going to be equal length. But our spring damper is not going to be equal length. It's going to be able to compress and extend. That's very important. Right. The other thing that we could do, we can create this line here. I'm just giving it kind of a starting position so that when I make these two equal. Okay. All right, and then need to just make this mount up to that. I need to make these two lines equal as well. You can see everything becomes fully defined. Now what I can do is I can figure out, I can get a driven dimension going off of this. This is my spring length when it's fully, so we're at full compression. My spring length is now 171 millimeters. We've compressed an inch of the spring with our full compression of our outboard suspension. You can also measure the angle, or kind of this angle here. You've diverged about maybe 2 degrees off of that ideal. You can also measure the distance between that there. So we have a force that's going over a moment arm length of 2.43 on that edge of the bell crank, and so that's going to cause some slight out of plane, or out of, how would I say this, non-ideal loading. But yeah, so I just showed how we can pull one dimension out from this complex system, but we can pull a lot of other dimensions out. And yeah, I'll go into those towards the very end here. Yeah, so we just did front suspension. Let's do rear suspension. And kind of same fun times here. Let's get both sets of control arms up again. Let's also, I don't think we need that anymore. We do also need our rear wheel assembly. And for now, I'm just going to hide front belt crank and rear belt crank. I'm just going to hide both of those. Some more water. All right. So let's just get right into it. This might also be a Solidworks thing where in 3D sketches, if you double click, it just keeps trying to draw lines and then it realizes, oh wait, you just double clicked. So we need to stop the line tool, but it keeps the lines in there. Not sure if that is a bug. Okay, so let's set up our initial. Perpendicular. Jeez. Okay. Same thing here. I'm going to split that. Now we're still on the good reminder to double check which plane you're on. Make this parallel to the rear axle center line. Okay. We're also going to do this here. Again, we're just kind of going through and adding relations. Equal lengths as much as possible. Then when we need to, we'll create stuff like parallel to the rear axle center line. One of the other reasons we're doing this parallel to rear axle center line is because basically we're trying to find the lowest point of the tire, and that's what we're moving up and down. At least that's the kind of assumption that we're going with here. Cool. And these two need to be perpendicular. All right, what are we fixed on? Can I not drag this? What's going on? Let's rebuild real quick. Weird. I think I have a lone or a stray constraint somewhere. Do. Okay, so it does a rebuild. All right. What I need to do is just figure out which of these I need to break in order to be able to move that up to where closer to where it's supposed to be. There we go. Okay. Perpendicular, and last but not least, from that to the midpoint, 50 millimeters. That's a right height. There we go. Yeah, okay, we're now at 80. That's where I want to be. Okay. All right. Home stretch. So yeah, we got that all figured out now. We can close out of the rear, so we don't need the chassis side view anymore. We can hide both sets of control arms. We can show our droop control arms, and we can also show our rear bell crank geometry. Again, from here, got to create those extra helpers. Go ahead and do that. Collinear, collinear. Hold on. Why not? Let's see. It really doesn't want me to do that. Why? That would make sense. It's because I drew on the wrong plane again. So, I kind of touched on this last time, but just wanted to hone in on it again. When you're drawing within a 3D sketch, it's very important to keep in mind, specifically when you're drawing lines within a 3D sketch, it's really important to keep in mind what plane, like the ZX right now, that's what it's thinking that I'm starting to draw on. And you can kind of see that when I pan around, this thing is kind of on the ZX plane. But if I look from the Y, or somewhere else, I'm looking along the ZX plane, that line kind of disappears. Kind of hard to show there. Basically, the main thing to keep in mind is that as you're drawing this stuff, make sure that you're if you start to draw something on like the XY plane and then you tell it to snap to Z, it's going to need to move quite a ways, and it's not going to move in a very predictable way either. And then the solver will kind of throw that error that we just saw. So yeah, I guess be cognizant. Keep in mind this triad in the bottom left corner. I'm looking at YZ, so if I'm sketching stuff out, it's probably want it to start on the YZ plane, or roughly. Yeah, hopefully that makes sense. Again, it's kind of one of the things that you'll pick up as you start to do more within 3D sketches. So right now, ZX, that's not the plane that I want to be drawing on. Well, actually, I could just draw on these real quick. No, I do want to actually be on YZ here. Okay. Yes. Oh yeah, I need to draw that line in as well. You can see it's struggling to connect because right now it's trying to draw on the YZ plane, and this needs to go pretty far along in X to meet up with that. As soon as I switch to a plane that has kind of X in that dimension, snaps right to where it needs to be. Okay, ZX. Sure, I'll stay in this plane for a little bit. Do that. And then, last but not least, we'll go back to XY. And those should be all of the lines that I need to draw. Cool. So now I can do all my collinear mates, and this should all snap in pretty smoothly. Actually, before I do that, I should probably make things the right length. So I'm going to hide that so I can see which lines I need to focus on. just take a quick peek. Which line did I say that was equal to? Things are getting confusing. Okay, yes. So yeah, if I look at each of these, they should all only have one mate. And last but not least, we'll get that one equal. Okay. Make those two, no, not equal, collinear. And that there, collinear. Everything snaps to black. Lovely. So, we'll also bring back our rear bell crank midplane. Show that. Because these next two lines we're going to draw, we're going to start on XY. Just these next three lines we're going to draw. 4. Cool. So all three of these need to end up on this plane. I wonder if I can. Yeah, all of them on plane. Cool. This line is then going to, or that point is going to be merged with that. This is going to end up being coincident to that. And then we'll do our equal lengths here. So that's an equal length. That's an equal length. That's an equal length. And then we'll also make sure that this endpoint here goes there and is coincident. Then, last thing we need to do is make sure that the distance between these 2 points never changes. So, same drill as before. Draw a construction line between the 2 points. Make it equal. Everything's fully constrained now. And we can also, like I showed before, we can pull out what our fully compressed spring length is, just as an example. And again, everything is just driven off of this dimension here. So, yeah, that's pretty much it. At this point, let me get some water. Right, so from here, what you'll do in order to design your bell cranks is you'll go through and you'll figure out, essentially what I did is, I guess I'll put it that way, is I plotted a couple of points. Full droop, where I wanted my wheel rate to be 0, and ride height, where I knew exactly what my wheel rate should be, and then full compression. So those 3 points, those define a curve, because they're not going to be linear. Those define a curve, or some kind of general trend. You'll want your wheel rate to increase progressively as you increase travel. And so from here, you do some very simple static analyses. And what I mean by static is we'll say, we're in a steady state corner at equilibrium. Here's how much our wheel has moved up, and then here's how much our spring has compressed. And so you just map those two against each other. At ride height, you pick out what your spring rate should be. And that's based on, so we'll say, remember, at full droop, our spring is fully extended. At ride height, we've now compressed our spring basically 15 millimeters here, right? So, so we've applied this much force to the spring, or this much force to the wheel, and here's how much our spring is deflected. And then basically what you do is you take you solve for the force going through the push rod, or basically you solve for an equilibrium of forces with this system here. And it's a little challenging. And again, you can make some simplifications as well. The stuff that I did in this design, I simplified a lot to say, we're just going to look at this in 2D mostly. We're just going to say, this is acting on that plane, so here's this angle that we're affecting this force on. We can do equilibriums. One of the other things you can do is you can get XYZ you can set this as a vector, set this as a vector, balance them out. And you can really go in depth, or you can simplify. It all depends on how confident you are with some of your math. And again, ultimately, what we're trying to do is we're trying to figure out, all right, well, what's a reasonable wheel rate curve for us to have? And that's something that's tricky. That's something that you'll want to probably consult with industry on. Kind of go through and say, well, I think this is reasonable. What do you think? And they'll kind of give you some feedback. Within the team internally, we have a few resources that we can talk to. But generally speaking, once you get to this point, you're playing around with these values. You're plotting things in Excel. You're doing some math to say, hey, here's my wheel rate curve. That's kind of where I'll leave you there. But again, at this point, you can create all sorts of different. You can pull out all sorts of different dimensions. You can also measure things like, if I wanted to verify that my camber angle. Let me expand this real quick. So I can dimension. Maybe I can't. Create a vertical line along Z. I'm going to create a dimension between these two. Cool. I'll pull this out. I'll also make this. So this is and remember, at right height, we had our camber angle at 1 degree. Cool. What's our camber at full bump? All right, well, it's 2.19 degrees. There we go. What is it at full droop? It's pretty much 0 at full droop. So we can start to evaluate some things like that. We can evaluate, like I said, our camber gain there. We can start to create construction lines, generally speaking, within, how do I say this? Within 3D sketches, things are very hard. It's very, very hard to create dimensions between lines and all sorts of stuff. So, create some construction lines for yourself that will help you create dimensions. You can also create planes within your within a 3D sketch and map things onto planes. I'm not really going to get into that too much. One of the other things you can start to look out for is, potential interferences where you start to see two lines getting too close to each other. That might be, a reason to readjust some of your earlier packaging sketches, that kind of stuff. So, I guess at this point, that's pretty much bell crank design complete, as well as that parametric sketch. The last thing we're going to talk about is steering, and steering tends to be an afterthought a little bit, at least it was in this case, or in our case this year. That being said, steering setup is fairly straightforward, and we could theoretically include it in the parametric analysis sketch as well. We could do some evaluation for bump steer. We didn't do that in last year, mostly because what we did last year is we set our steering link to be along the same plane as our lower control arm, and that completely negates bump steer, effectively at least. You get very, very minimal, imperceivable bump steer, but by creating your steering link on the same plane as one of your control arms, you're basically, or I guess the theory behind bump steer is that your instant center, the instant center of your two control arms, wherever that intersection point is, your steering shaft lies. If you were to project the line of your steering toe link, that's the word. Your toe link, that would intersect that point as well. And as long as it stays along that point or very close to that point, your bump steer is minimal. And one of those ways is to just make it along the same line or plane as your control arm. So, that being said, generally you design, when you go about designing steerings, you'll go through and my brain is just toast. Right. So when you go about designing your steering, you start from a top-down perspective, generally speaking. And on that note, actually, let me do something here real quick. I'm going to do, since we have, we're going to put all this together into a folder. Let's say this is bell crank design or creation. We're going to hide that plane. We're also really quickly going to create a 3D sketch of both sets of bell cranks, or bell cranks, spring dampers, and push rods. And I should really hide that, so let's do that. And this will be off of, well, I guess we should really be going off of the, oh no, so we're creating things at right height. Yeah, so really quickly we'll create, I don't know, we'll actually go through that at the end. Yeah, that makes more sense. Okay, so we've cleaned all that up. When we create our steering, generally speaking, this is done from the top-down view. I'll go back into what we did last year. Steering, top view, and we'll take a look at this sketch really quickly. Essentially what we did here was we figured out where our steering rack is, and this looks a little bit confusing here. Yes. Sorry, like I said before, my brain's pretty fried after a long day of work, so we're kind of working through this stuff. All right, let's get both sets of control arms back up, and then we'll hide parametric analysis. We'll also hide our bell crank geometry. Cool. So what we need to do is we need to create a construction line that's coincident with those two, right? So, and that kind of sets up this line right here. From there, we're going to also create, I guess technically I'll just go off of there, and then I'll create a midpoint line. And this will be our actual steering rack. Wrong keyboard shortcut. Essentially what we did here was we offset our steering rack 50 millimeters in front of our front control arm point here. And from what I remember, we decided on a length of our steering rack itself. Let's go back to this here. It was 538, and it was actually 40 millimeters in front of that point. Yes. I'm trying to remember how and why we did some of this stuff. Okay, so we had our vertical line there. Push that out 2 millimeters. Why? I should know this because I did the design. So there's a chapter in Race Car Vehicle Dynamics that outlines, you pull it up. Yeah, no, I don't want to open an edge. Let's pull up our team scanned copy here. Only using it for internal purposes. Yes. Oh, geez, come on, Windows. Focus. Steering. Trying to remember which chapter steering is. I think it was somewhere around chapter 15. No, it's applied arrow. Steering systems is 19. That's right. So page 709 is what we're looking at. In our case, we were going for parallel steer with perhaps a touch of reverse Ackerman. And yeah, the things that we saw basically. This is part of stuff that's a little bit fuzzier in my brain. Yeah. Essentially, if you want to find out more about steering systems, it's outlined in Chapter 19. And from what I remember, a lot of this is fairly trial and error. And yeah, I think that's what we ended up doing. We ended up doing trial and error to where we saw at max lock kind of what were we seeing. And we could also do this for less than max lock and more than max lock as well. We can go back and forth. And as we can see here, fully the inside tire at full lock is doing 24.6 degrees, while the outside tire is doing 26. This is slightly closer to, or this is slightly reverse Ackerman, because again, the outside tire is turning more than the inside tire. This is outside, this is inside. Yes, that's kind of how we did it. And then we also simplified things in the outboard side. And I'm going to pull up the lower control arm mounting point here as well. Both sets of control arms. Yes, so this was coincident to that. And that's, again, theoretical as well. So, going from here, what we do is we create, I got to remember which one's my lower control arm. There we go. I'm going to create a vertical line. This is going to be coincident there. I'm going to go back to our normal view here. I'm actually just going to go ahead and rotate this around. So we're looking at it more like that. Again, in our case, we measured this way here. Okay, this is 40 millimeters. This is 2 millimeters. And that was kind of based on our upright geometry. And then that sets your steering linkage. You have your, the width of your rack. You have where it's mounting up to you on your outboard assembly. And again, this is also with assuming straight ahead static toe. So you'd adjust your toe link or your steering link here to compensate for your toe. And then again, from here, essentially what you do is you figure out how far your steering rack can go. And in our case, this was, let's see here. It's 39 millimeters from lock to lock. And we'll do the same thing here. I'll make another point. Another neat tool here, select other. This way, if you can't select the line you want, you can still do it. We'll make those two equal length. That's what I wanted to do. We're going to create two dummy steering links here. And theoretically, we could also go through and do this in a separate sketch if we wanted to do this for clarity's sake. All three of these are going to be equal length. All three of these are also going to be equal length. And that's right. So this needs to be 39 divided by 2. So that's from center to lock on one side. And now we can evaluate, all right, well, how much are we turning one way versus how much are we turning the other way? And in this case, you can see it's pretty big reverse Ackerman. So we can adjust some things here. We can tweak some dimensions and figure out where we want to put our steering link in order to make this closer to parallel steer if that's something that we wanted to do. But again, this is also a guideline. We're making some assumptions here because we're looking just from the top down. And what we're actually going to do is we're going to create a plane that is comprised of our lower control arm links. Okay. And then we're going to create a 3D sketch with a line that is on that plane. Actually, I didn't need to. I'm going to showcase the 3D sketch plane tool really quickly. It's this one right here. I can click, I can create a plane just like I would any other time. I just had 2 lines there, and now I'm in, I have this like graph paper looking thing, so it's a plane that I'm drawing on right now. Anything that I draw while I'm seeing this graph paper will be on that plane. If I double click off of the graph paper, you can see kind of an outline of it. And then if I double click on the border again, I can get back into that. So again, this way, this is on that plane. You can see there's a relation for it there. Now what I need to do is I need to make 2 vertical lines. I'll make one on the YZ plane there. And you can see as I start to do this, it's going to tell me that that's along Z. That's along Z. This is going to be coincident with that point. And this is going to be coincident with that point. And we've created our steering link. So again, we've looked from the top down. We've done some quick math to figure out roughly, all right, we're kind of looking at reverse Ackerman here. Okay, cool. That's kind of what we want because we're building race cars and we're not building street cars that are driving slowly around parking lots or horse carriages on gravel roads, which is one of the analogies that RCBD makes. And in the textbook, Race Car Vehicle Dynamics by Millikan and Millikan, highly recommend. Yeah, so we've made some assumptions. We've made several throughout the course of today's video in my scattered brain. But like I said, from here we've created a full suspension geometry, we've created our steering links, and ultimately I highly recommend that you take this and you input it into a SimScape multibody or other full kinematics solver, even just a full Solidworks assembly where you create all of these points and then you start pushing it through different motions and getting hard data on, well, this is actually how much my spring is compressing. Well, this is actually how much my bump steer is. Well, this is actually how much Ackerman I have, so on and so forth. Again, you could do all of that. My goal here was mostly just to show, again, this is kind of how I did things last year, and you can take it from here. And hopefully I've left enough room for people to go through and do that and haven't confused you too much. Again, that being said, if I have confused you, my apologies. You can always contact me. My information's in the description below. Steering, we'll do top view steering. And then this is left steering link. All right. Cool. One thing to always, or I guess last thing we'll do here, we'll set everything to right height, and this is something that I try to do after I'm done with all my parametric analysis here. Set everything back to right height, exit out. We're going to go through and we're going to just create one final sketch. And this is just something that I do just to kind of keep everything, if you want to just hide all the sketches and then you have one sketch that you can show in your full car assembly that says, hey, here's where the suspension links are going to go. We haven't actually put hard tubes on them yet, but here's the geometry. It'll at least show up in an assembly. So yeah, last thing is just to go into a 3D sketch. And then instead of doing that, I'm just going to show left side of control arms. We're going to select our control arm geometry, our steering link. We're going to convert all that. We're also going to go through and take both of our bell cranks and show both those sketches. We're going to take our pull rod, our damper. Actually, that's at Droop, so actually we need to do this in our parametric analysis. All right, got those, and then we also have these. On second thought, so the reason why I was going to just go through and pick our static control arms is just so that everything was at right height, but you might find a use for showing your suspension geometry in in full droop or full bump in a full car assembly or something like that. The only thing, remember, that we didn't do is we just did static right height steering link. So and hopefully with the if you were following along or with the information I've presented here, you kind of know how you might go about setting up the top view steering or the steering link in the parametric analysis. If you did both of these steps beforehand, before the bell crank creation, for example, that could be one way of doing it. And then remember, you just fix this inside point, you make this parallel, and then you create some geometry to tell it how to relate to the wheel, at least roughly. So again, we'll convert all these entities here. Cool. We'll hide the parametric analysis sketch. We'll also make a line there because that didn't transfer over. We're going to select everything. We're going to mirror it across the side view plane. There we go. Cool. And we can exit out of that. Hide both of these sketches. Group that together. Steering link creation. This is suspension wireframe. And Shift C collapses our entire Shift C will collapse our entire feature tree down to that. And this is why I like putting things in folders so much. My biggest tip for anybody out there, if you're not going to go through and rename every single feature, which doesn't always make sense, or rename every single sketch, which doesn't always make sense. In this case, it does because we're doing a lot of sketch on sketch on sketch on sketch. But again, you're not always going to be renaming everything. At the very least, put things in folders and rename those folders. And then that way you can also collapse and say, all right, well, here I was working on constraints, or, I just got done working on steering links, but I need to go change something within the control arms. Oh, okay, yeah, here we go. Right. So that's kind of where we're at. I think I covered everything that I wanted to cover today. And from here, it's kind of in your hands. You, the viewer, can now take the next steps. Like I said, my contact information is below. If you need to get a hold of me, you can do so through LinkedIn. If you're watching this from the Viking Motorsports team, I'm still on the Discord for now. So if I'm still on the Discord, you can always contact me there. I try to keep a good eye on it. Again, things might change. Discord might go out of style in 2 years or whatever else like Slack did. So, thanks everybody for watching. Let me know if you have questions, and hopefully this wasn't too scatterbrained.